Hi everyone, my name is Xiang Fei. I'm a resident senior at the Chinese University of Hong Kong, Shenzhen, and I'm now a Robotics Institute summer scholar at the Biorobotics Lab in Carnegie Mellon University, supervised by Dr. Howie Chauset. And today it's my honor to give you a presentation about my research during the summer program, Bag of Work Groups, a robust loop closure module for impact Visual-Laser-Inertial SLAM. The first is about the background. Impact simultaneous localization and mapping techniques have the potential to facilitate pipe condition inspection and anomaly localization. As you can see in Figure 1, through dense RGB-D reconstruction, we can clearly see the welding seam, section view, and hole in a pipe. And our team has developed the confined-space dense RGB-D SLAM method via SLAM, which can be used in narrow pipes and have achieved promising results. However, as you can see in Figure 3, during our experiments, we found that VI SLAM suffers unignorable accumulative drift in long-distance situations. Loop closure is vital in the process of SLAM as it helps to reduce the cumulative drift. And the basic idea of this technique is to check whether the robot comes back to a place that it has passed before. If so, we can establish the connection between the current frame and the loop closure frame. And then we can actively pull the trajectory back to reduce the cumulative drift. Also, since pipeline networks often compress one or multiple loops, loop closure is suitable and valuable for impact SLAM method to generate a globally consistent map. However, in pipe environments, conventional loop closure methods suffer perceptual aliasing due to feature scarcity and textural repetitiveness. Perceptual aliasing means many keyframes in different places look very similar. As a result, it's difficult for conventional loop closure method to correctly perform loop detection. You can see Fig 6, the place 1 and place 2 have very similar appearance. Typically, we have two strategies to solve this problem. First is to detect richer features, and the second is to extract more discriminative information from existing features. Our research goal is to first develop a robust loop closure module in pipe environments with high precision and high recall. And we have finished this work during the summer. And in the future, we want to incorporate our module into the existing VI SLAM system to achieve high localization accuracy and mapping consistency. Overall, we have three main contributions. First, a feature detector capable of detecting features at different scales based on an image pyramid. And second, the definition of work groups exploiting the spatial co-occurrence of detecting features, which provides context-specific feature representation. And in addition, a database is established and updated online, storing the workgroup information of each image, which enables efficient loop closure scores computation. And combine all these works, we successfully developed a robust loop closure detection module in pipe environments. And then it's about some related works. First is bag of words build-up. This technique is originally used in text retrieval and now has been widely adopted in face recognition. And a visual word vocabulary is created by clustering the extracted features from a set of training images. And each image is represented as a histogram of visual words. And each bin is the frequency of a word in the image. After we obtain the visual word vectors, we can directly compute the similarity scores. And then is term frequency, inverse document frequency, TF-IDF. TF-IDF is the way that reflects the importance of each word in an image. It is the multiplication of two terms, term frequency TF and inverse document frequency IDF. And TF-IDF considers the weight of a word according to the frequency of the word in the image and the frequency of the word in the vocabulary. It is beneficial for us to better distinguishing these different images. Also, for the strategies to solve perceptual aliasing, as I said before, first we can try to detect richer features, and there is a research suggesting that the group feature to track method is suitable for pipelines. And also, we can mine more discriminative information from existing features, and there is a research to utilize the relative spatial co-occurrence of features in pair to enrich the information we obtained. And this work achieves promising results in topological map. In our research, we consider both the two strategies, And this is the framework of our proposed BoWG-based localization detection method. And two novel modules are proposed: multi-scale group feature to track MS-GFTT and bag-of workgroups BoWG. For the workflow, first, when a new keyframe is detected by the SLAM system, the proposed MS-GFTT method is applied to extract visual features with different sizes and use grep to compute the feature descriptors. After that, the obtained feature descriptors are utilized by DBOW2 to gather words in the keyframe and use TF-IDF scores from DBOW2 to obtain the localizer candidates. And here, DBOW2 can be replaced by other bag-of-words methods. After getting the size, coordinates, and corresponding words of each feature in the keyframe, the workgroup information is analyzed. And this information is utilized by the BoWG module to obtain the BoWG scores of the localizer candidates. After that, the BoW2 scores and the BoWG scores are combined to compute the similarity between the keyframe and the localizer candidates, then choose the final localizer frame. Finally, new work groups in the current keyframe are added into our BoWG database to perform an online updates. Now I will introduce the details of the two proposed modules. For MS-GFTT, the motivation is to extract richer features in the keyframe and provide a size for each feature point to support subsequent workgroup analysis. And first, Gaussian kernel is utilized to downsample the input keyframe and the mask and form the Gaussian parameters. After that, we perform GFTT on each layer of the Gaussian parameters to detect features with different scales. And then it's about the definition of workgroups in our research. We define three different types of workgroups based on the spatial proximity and positions of features. First is the multi-scale features, which means the feature can be detected in different layers of the Gaussian parameter. And then is word pair and the word triplet, which means the distance between different features is less than the sum of the radius of these features. And the same word group contains the same word and located in the same area of the images. Then is the data structure design of our BoWG module. And to implement this module, 4 different types of tables are required. First is BoWG vector, which is a representation of each image and is used to compute the similarity score between different images. Each image has one BoWG vector. The underlying data structure is map, and the similarity scores of two images is as the formula shows. Then is BoWG tables, which stores all the workgroups detected in the previous keyframe and their information. And the underlying data structure is multi-map. The reason we use multi-map is that workgroups with the same keys may be different workgroups since they may locate in different areas of the images. Therefore, different workgroups may have the same key, and workgroup ID is the only identifier of each workgroup. Then is direct table, which stores the BoWG vector of each image and is used to compute the similarity scores between the current keyframe and the localizer candidates. The underlying data structure is a vector, and then is IDF table, which stores the number of each workgroup in the database and is used to compute the IDF value. The underlying data structure is map. By using the designed data structure, we can efficiently compute the localizer scores. Then is the combined score that is used to finalize the localizer frame, which takes into account both the DBOW2 score and the BoWG scores, and considers that the workgroup matching is much stricter than word matching, and the workgroup information in each image is rich, so the TF values of BoWG score is significantly smaller, and the difference between high and low BoWG score is much greater. Therefore, we decided to use min-max normalization to process BoWG score and use it as a factor to multiply with the DBOW2 score to get the combined score. And in this way, the combined score has 3 characteristics. First, images with higher DBOW2 and BoWG scores still have higher combined scores. And second, images with higher DBOW2 score but lower BoWG scores will have lower combined scores. Finally, the difference between high and low final scores will be much greater. And these characteristics help us to against perceptual aliasing problem. Okay, now let's talk about the experiments. We consider 4 small areas, A, B, C, D, in the pipeline with loops, as this figure shows, and each area contains 10 frames. And suppose the robot returns to area A and collects a new image. That is, area A is the loop closure area. And we calculate the similarity scores of the previous frames by comparing with the new collected image. And we expect that the scores in area A are higher than other areas. Also, we conducted experiments when BCD is the loop closure area, but they will not be included in this presentation because of time and space limitation. We also defined 2 more metrics, average score difference ASD and highest score difference HSD, which helps to reflect the ability of the method for distinguishing the true area and other area. And also, higher HSD reflects that we can adjust the threshold over a larger range to obtain at least 1 true loop closure frame without errors, which is beneficial for us in practical use. This figure shows the similarity scores of different areas obtained by different methods. You can see that when we use the previous method, GFTT plus DBOW2, some frames in area C score higher than area A, which may lead to an incorrect selection of loop closure frame. But when using our method, area A scores significantly higher than all other areas. And these 2 figures illustrate the precision recall curve and the ASD-HSD values. The table shows the detailed results. You can see that the ASD-HSD values of our method are much higher than other methods. Besides, our method can achieve significantly higher precision while with acceptable recall. In addition, our method is fast enough to perform online updates. We also conducted robustness test, and we still consider area A as the true loop closure area. We randomly perform small data augmentation, like rotation, translation, scaling on 5 images, and the results barely change. We suppose that our method is robust and can cope with small changes in the environment. In addition, we conducted experiments on other environments. We tested on sequence Freiburg 1 room on TUM dataset, which is an indoor office environment. And we still choose 4 areas to analyze the performance. From the results, you can see that our method can still reach high precision with acceptable recall. Besides, the HSD obtained by our method is significantly higher, which means that it is much easier for us to set the threshold in practical use. Therefore, the proposed method has the potential to be applied on scenarios other than narrow pipes. Finally, this work was supported by the Department of Energy's RPIE repair program, Carnegie Mellon University Robotics Institute Summer Scholars Program, the BioRobotics Lab, Shenzhen Institute of Artificial Intelligence and Robotics for Society, and the Chinese University of Hong Kong, Shenzhen. We would like to thank Rachel Bursing and Professor John Dolan for their support and organization of the RISC program. I would also like to thank Tina Tian, Lu Li, and Professor Howie Chaucer for their insightful guidance. That's all of my presentation. Thank you for your listening.